So we just got done learning about Orsted's law, which tells us that the cause of magnetic fields is electric currents. But that raises some questions. As Professor Bitter in one of the videos you're going to watch pretty soon points out, what are the electric currents in this magnet? It's got to be something moving around inside the atoms. And electrons are easy to single out since we know they're the things that buzz around the outside of atoms. But that raises a question. Sure, this is made of atoms with electrons, and this coffee can is too. So it makes sense the coffee can would experience a magnetic force. But isn't this textbook made of atoms? No magnetism. This copper tube is made with atoms. No magnetism. No magnetism from ceramic or asbestos or chalk. So what is it about this magnet and this can that allow them to be magnetic? Well, if we're going to go back to Orsted's law and say it has to be because of moving charges, let's take a look at the electrons. It turns out that electrons themselves are actually tiny little magnets. Now, exactly how the electron is a tiny little magnet is way beyond the scope of this course. To really understand it, you need the type of science known as quantum mechanics. But if we think of the electron as being a magnet, it's got a north and south pole. And just like a little magnet whose south pole was pointing this way would behave differently than one whose north pole was pointing this way, electrons can behave differently too. And it turns out this idea of electrons with their poles oriented differently, it turns out that that's really helpful for understanding how electrons behave in an atom. We're going to see that there's two types of electrons we have to look at, and they essentially correspond to having their poles in different directions. This is called electron spin, and don't get too hung up on the directions I've got here. Just know that some electrons have their poles pointing in one direction and others have it pointing in the other. Chemists usually call this spin up and spin down electrons. What would happen if we had two magnets right next to each other? And we'll say that this one has north here and south here, and we'll put the other one opposite above it. A lot of their magnetic field would be canceled out by each other. So if you happen to have two electrons that are close together, and they're spinning in the opposite direction, in other words, their poles are pointing different ways, we expect their magnetism to not contribute that much. So as we go through and think about where electrons are in the atom, that's going to help us understand whether the magnetism from each electron is visible or whether it's canceled out by a nearby electron. Now, in order to figure out what is a nearby electron, we have to think about the structure of an atom. So we'll go with the simple Bohr model that you learned about in 9th grade science and at the beginning of chemistry. I've taken here a specific atom, lithium-6, and lithium-6 is going to have 3 protons since it's lithium. And since it's lithium-6, it will have 3 more things in the nucleus, 3 neutrons. But most importantly, it's going to have electrons going around the outside. Now, you're probably noticing that I made a ring here. And you probably know why. I'm going to put the electrons in to that ring. And you're probably also aware of the fact that I can't put my extra electron, because I need 3, in this ring. Where does all that come from? What does that all mean? It turns out that the ring, which is really called an orbital, is a measure of the potential energy that these electrons have. Electron's negative, it wants to be near this proton. So if you move it out, you have to do work. Just like if I want to move this textbook up, I had to do work. So this ring is a place I can put electrons, just like this chair is a place I could put the textbook, that's stable. And those electrons can be left there. It's almost like a shelf. We told you, though, that this ring, this orbital, only has room for 2 electrons. Here's your 2. One that's got its magnetism like this, one that's got its magnetism like that. One of the iron laws of chemistry is that you can't have identical electrons in the same atom. They have to have something different about each other. Either the shelf that they're on or the magnetic spin that they have has to be different for every single electron. So only 2 can fit on a shelf because there's only 2 different possible spins. So where would our 3rd electron go? It has to go on a higher shelf. And that shelf is going to have more energy. Just like, as I move the book farther away from the ground, it has more energy. And we always fill up the lower shelves first so that we can do less work putting those electrons there. Now, why does an atom have these shelves? Why are certain orbitals there and the other ones not? That's really a topic that you'll have to cover in chemistry. But atoms only have certain places that electrons can go. So let's look at this magnesium atom here. And you can see I've got the same rings I did in the lithium picture. And there's the 2 that the inner ring can hold. And you may remember that we claim that the second ring can hold 8. How does that jibe with the fact that we're saying there's 2 electron spins and each orbital can have 1 of each? It turns out that this is a pretty big oversimplification. We kind of lied to you a little bit there. The ring can only hold 2, just like we saw for the first one. But there's actually 3 more orbitals very close in energy. And these 4 orbitals together, they can hold 8 altogether. In case you've heard the term, I'm going to give these names. Don't worry about them if you haven't. This inner ring is called the 1s orbital. This next ring is called the 2s orbital. And these next 3 are called the 2p orbitals. It's important to understand that when we draw the ring in the Bohr model picture, it's a vast oversimplification. One of the strange things about quantum mechanics is that it's very difficult to nail down the position of the electron at any one time. We usually talk about where it's most likely to be. This Wikipedia user, Poor Leno, has plotted the probability or likelihood of the electron being in certain places for different orbitals. We can see that some of these orbitals have a spherical distribution, others have a very non-spherical distribution. This is all stuff you'll look at later in a chemistry class. But we use this idea of rings in earlier classes because it helps us understand what's happening with potential energy. So we'll stick with that notation. So we add electrons in one by one, and if we were going to add lithium's electrons in, our lowest energy orbital was our 1s, and then we had a 2s, and then we had our 2p's. So we add electrons in one at a time until we've got all our electrons put on some shelf. And just like we would want to put textbooks on the lowest shelf possible so we wouldn't have to do as much work lifting them, we're going to put electrons on the lowest shelf possible. Energy is increasing as I go this way, since I'm moving a negative away from a positive. So let's put lithium's 3 electrons in. So for lithium, our electronic structure diagram is an up and a down. That's these 2 electrons. And then we have one more that's there. So that's the electron diagram for lithium. And as you can see, we have an unpaired electron, which means we have one electron whose magnetism is not going to cancel. So we expect the lithium atom to be a tiny magnet. Now the material that you know is magnetic the most is iron. So we need to talk about why iron is magnetic. If you look at where iron is on the periodic table, it's in the first row of what are called the transition metals. If this is the overall shape of the periodic table, the first row of the transition metals are here, these shorter columns. I don't know if you've ever wondered why the periodic table has this shape, but it has to do with these allowed places for the electrons to go, these allowed shelves or orbitals. The two tallest columns, group 1 and group 18, those correspond to elements that are just filling the 1s orbital. The next, these are filling the 2s orbitals and the 2p orbitals, the 3s orbitals and the 3p orbitals. And now we get to here the 4s orbitals. Now we get another kind of shelf, which is called the d orbitals. If you look at where iron is on the periodic table, it's in the first row of what are called the transition metals. So that's a little bit farther down. There'd also be 3s orbital, and there'd be 3p orbital, and there'd be a 4s orbital, and then the first row of the transition metals, there's actually 5 of something called d orbitals. And all of these shelves below these d orbitals, lower in energy, are all filled up. So I'll just take a minute to fill those in, because there's a lot more electrons for these atoms. So now we get to the transition metals. And we kind of just count over to see how many d electrons there are in each transition metal. So scandium would have 1, titanium 2, vanadium 3, chromium 4, manganese 5, iron 6, cobalt 7, nickel 8, copper 9, and zinc 10. So that's going to help us figure out whether an atom is magnetic or not. So I think it's pretty easy to tell that zinc is not going to be magnetic, because zinc, it's got 10 electrons, and that's going to fill up entirely our 5d orbitals. So zinc should be non-magnetic. But a lot of these other ones could be magnetic. Let's start with iron. Iron with 6. Let's put 6 electrons in and see how iron could be magnetic. 1, 2, 3, 4, 5, 6. That would leave iron with a lot of unpaired electrons. And that would make the iron atom a magnetic atom, which is what we observe. It looks like we understand why some materials are magnetic and others are not, but the element that's going to rain on our parade is copper. Copper does not have magnetic properties. But if we look at where it is here with 9 d electrons, it feels like it should. We've already got 6 in here. Let's just add in 3 more for copper. 7, 8, 9. We still have an unpaired electron. So a copper atom actually is magnetic. But why don't we observe it? It all comes down to how the copper atoms themselves add together. It turns out that with copper, when you have an atom exhibiting one type of magnetism with its north pole in one direction, the ones nearby are going to tend to line up to cancel its magnetism out. They're going to put their north poles in the opposite direction. There's only some materials, and iron's one of them, where they tend to grab onto each other and align their magnetism in the same direction. Now, it doesn't happen across the whole material, but there's little areas where everybody and their neighbors all have their magnetism pointing in the same direction. Those are called magnetic domains. So, one last question. This thing sticks to steel stuff. It's a pretty strong magnet. My coffee can doesn't. But they're both made of iron. So what's the deal? What makes this magnetized and that not? Well, like I said, iron has these little domains, these little regions, where neighboring atoms reinforce each other's magnetism instead of canceling. But those domains are still very small spaces in an iron atom, or an iron material. So even though everybody here may all have their north poles pointing in one direction, next door it's going to be different. And next door it's going to be different. And everybody's going to be in a random direction. Because all the domains are pointed in random directions, this piece of iron or steel doesn't appear to be a magnet. And that's consistent with a lot of the iron or steel we see in our lives. But this can be magnetized. And the way you do it is to put a strong external magnetic field, which I've got labeled B here. You'll notice that some of these domains are lined up with the field and others are not. Let's see what happens when you do this. These are two not very impressive bar magnets. You can see from this oil and iron filing mix I've got on top of them that they're barely making the iron filings line up along their magnetic field lines. But that's pretty easy to fix. All we have to do to magnetize them is put them in the presence of a strong magnetic field that lines up with what we want their domains to line up with, and they'll turn back into being strong magnets. So that's what this device here, the magnetizer, does. So what we're going to do is we're going to take our magnets. We'll put the south in like that. We'll put the north in like this. We'll put just a piece of metal over it. Turn it on. Give it a press. And now we'll check. As you can see, there's a fairly strong magnetic field, and these magnets will once again be useful objects. What happened? Well, the bar magnets originally were like this picture. Their domains were pretty randomly arranged, but some of those domains were aligned with the field, some were against it or not on the field. And as time passed in the strong external magnetic field, it was energetically favorable for atoms to switch from being in this domain to being in one aligned with the field. So in other words, this domain grows at the expense of these two. And we get something like this. At the end of the day, we're left with lots of atoms and lots of domains pointing in the direction of the external field. So we've now magnetized that piece of iron. It will behave as a magnet.